Hi guys. So in this video, we have three questions still to talk about as far as the whole kinetics unit goes. In this next video, we're gonna look at questions 1 and 2, which are why some reactions happen faster than others, and how we can show this using a graph. So, before we get into what the graph looks like, we need to talk about what activation energy is. And I always think of like when you get a new cell phone, you have to activate it, like you're starting it up for the first time, you're turning it on. So, activation energy is defined as the amount of energy it takes to initiate or start a reaction. That says takes. So these are two examples, and I'm actually going to show you demonstrations the next time we get to class. KMNO4 plus glycerin, if these are my two reactants, they have a pretty low activation energy, so they don't need much for effective collisions to occur. Where magnesium plus oxygen, this has a pretty high activation energy. Again, I'll show you this the next time I see you in class, but we have to apply a significant amount of heat to magnesium to break its bonds in order for it to combine with oxygen. Where with KMNO4 and glycerin, we really just have to mix the two together, and they kind of just start reacting. So what that looks like on a graph, these are called potential energy diagrams. And the y-axis is always going to be labeled potential energy. And the x-axis, it's either, I've seen it as reaction coordinate or time. So as you go across the x-axis, that just means that time is going by and your reaction is proceeding. You're turning from reactants into products. So our reactants always start with a certain amount of energy. So that line is going to represent how much energy our reactants have. Now, activation energy is the energy you need to add to the reactants in order for their collisions to be effective, in order for them to have enough energy to effectively collide. So if we're adding energy, it makes sense for our line to go up. So we show activation energy by making a little increase, followed by a decrease, followed by that. Okay, my hand is a little shaky, guys, but those lines should be straight. So that's a low activation energy compared to a high activation energy. What we want to do is we want to just make this hump higher. Okay, so we're looking at this area, how high the hump goes, versus in this reaction, how high the hump goes. So it's going to be harder to get the Mg and the O to react compared to the KMNO4 and glycerin. We need to add more energy. Okay, so these are called potential energy diagrams, and they're a little bit more complicated than what I'm showing you right now, and we'll get to that in a minute. Why does activation energy exist? So let's just look at the Mg and the oxygen example. In a strip of magnesium, I have metallic bonds. These atoms are all held together by bonds. The positive ions and the negative electrons are attracted to each other. And in our oxygen molecules that are in the air, I have these nonpolar covalent bonds. And before Mg and O are able to combine with each other, the Mgs have to break apart from themselves and the Os have to break apart from themselves. So if we think about BARF, which is something we talked about a couple units ago, if I want to break bonds, B, I have to absorb energy. So that's your activation energy. You're breaking up the original bonds that exist. Now, when I form new bonds, energy gets released. So as I form MgO compounds, that energy that I added is going to start coming back out, okay, as I make new bonds. But that's what the original amount is for. And guys, that explains why the graph comes back down after it goes up. Once I break my original bonds, my new bonds form and energy is going to get released. So potential energy diagrams are always going to have this shape where first we go up and then we come down. Okay. So like I said, there's more to these diagrams than I had originally mentioned. You're going to have to be able to look at a potential energy diagram and label all these parts. And the arrows won't always be in the same exact spots, and they won't always be labeled the same exact way. So let's talk about this part of the graph that we just kind of did. We already know that that's the activation energy, right? So we want to say, okay, well, which arrow in this diagram represents that exact amount of space? And I see that arrow A represents that. So A would be my activation energy. Now notice that this is labeled the forward activation energy. So we read left to right. That's how we read the graph. We're going to start from the left and go to the right. The reaction is going forward. The reactants are turning into products. So that's what A is going to represent. You might see a diagram labeled in a different way, and they might have an arrow that's labeled B representing activation energy. So you don't want to be memorizing that A is always going to be activation energy, because these graphs can be labeled in a million different ways. Okay, so let's kind of go through it from left to right, and I'll explain what each part represents. Okay, so what we're starting with, come on, erase. All right, I'm going to leave it there. We're starting right here, right? And this is the amount of energy that my reactants have to begin with. Now, if I had to choose a letter that represented how much energy these reactants have, I want to notice that arrow B is touching the reactants, and it goes all the way down to the bottom of the graph. So that's showing in total how much potential energy those reactants have. So that first part of your graph is always going to be the potential energy of the reactants, right? We talked about A already, which is us adding energy to the reaction to get it started. That's my activation energy, okay? Now, I want to talk about D, which is the potential energy of the activated complex, also known as the transition state. So guys, right here is where your effective collisions are occurring. Here is where my reactants have enough energy for them to break their original bonds, and they haven't formed new bonds yet, but they're getting ready to. They're transitioning into products. So they have the most amount of energy at this point, and arrow D is representing how much energy that is. So it's called the activated complex. Okay. Notice that now my graph is sloping down, because as we're forming products, as we're forming new bonds, energy is being released. And here are my products. Again, guys, even after the chemical reaction stops and all my products are made, the products themselves will always have a certain amount of potential energy stored inside of them. So which letter do you think represents how much energy the products have? That would be F. Okay. Now, for some questions, we don't really care about the process. We just care about where we ended in terms of energy versus where we started. Okay. So think about driving to school, right? Let's say that your parents, you get in the car and you go straight to school, right? And your house is 1 mile away from the school. So you end up 1 mile away from where you started. Now, let's say the following day, 2 of your friends call you and they need a ride to school. So you get in your car and you go over to this house and you pick that person up, and you go over to that house and you pick that person up, and then you end up at the school. You traveled a lot further the second day, but you still ended up 1 mile away from your house. We didn't really care about the path you took, right? So heat of reaction, or enthalpy, or delta H, so you could see it written as any of those three ways, is really just saying, I don't care about this whole part. I just want to know where I started versus where I ended. And arrow C in this picture shows that difference, that net change. So C is going to be my heat of reaction. Now, if I'm looking at a difference, guys, I want to know if I had to calculate this difference, how I would do that. So difference is subtraction. And it's a very, very important formula for you to remember, that you always want to do the PE of the products. That has to come first, minus the PE of the reactants. If the y-axis was numbered, you might actually have to calculate this by subtracting those two numbers. But for some reason, the chemistry regents loves to ask you this formula. Not do anything with it, just what is the formula? And you have to know that it's products minus reactants in that order. We're going to get into this in a little bit, but if I just look at this graph, I see that my products are actually lower than my reactants. So in math, if you take a small number and you subtract a big number from that, you're going to get a negative answer. Yes? So in a couple slides from now, we're going to see why a negative answer, what a negative answer tells us about a reaction, because it tells us something. We don't always end up lower than what we started. All right, finally, guys, we have reverse reactivation energy. Now, this is something we have not talked about yet, but some chemical reactants are reversible, where reactants turning into products is the forward reaction, but then those products can turn right back into reactants, and that's the reverse reaction. You'll know a reaction is reversible if you see a double arrow in the middle like this. But guys, if you see reverse, that just means you want to read this graph from right to left. You want to read it backwards. So if I'm starting here, I have to climb this hill to get the reaction started. I have to go back in the other direction. So which letter on this graph best represents the amount of energy required for me to climb this hill? E. So if I wanted to go in reverse, I'd have to add that much energy to get the reaction going back in reverse. Okay, so these are all the parts that you need to know of a potential energy diagram. How does a catalyst change a potential energy diagram? So when we defined catalyst in video 1, we said that it gave the particles an alternate pathway, right? So alternate pathway, I'm going to write it again because it's important, with a lower activation energy, meaning my particles are lined up so perfectly that they don't have to have that much energy when they collide. So if you guys think about what part of this graph is the activation energy, it's this right here, right? So what that's going to do is that's going to get lower. So typically you're asked to show how a catalyst will change a potential energy diagram by drawing a dashed line. As long as you draw a line, or I'm sorry, it should actually be like a bump, but it's lower than the original bump that's there, then that's acceptable for the new pathway that a catalyst will provide. Notice that where my products are, my reactants are, and where my products are aren't changing, okay? You're just giving a shortcut to get there, okay? The activation energy and the activated complex all get lower. All right. So, table I is a list of a whole bunch of different chemical reactions, and it gives you the heats of reaction. It gives you the delta H's of all these reactions, which is this middle area, this C, where my products are compared to where my reactants were as far as energy goes. So I want you guys to notice that for all these delta H's, we see positive and negative signs in front of them. Underneath table I, it tells us that a minus sign indicates an exothermic reaction. So if we don't have a graph, we can just look at this number and say, oh, I know if the reaction is exothermic or endothermic. So let's make a little chart here. Exothermic means that I released energy. It means that the products are lower. Endothermic means that I absorbed energy. It means that my products are higher than my reactants. Okay, I want to jump down to looking at a potential energy diagram. So guys, what I mean by lower and higher, my reactants always start somewhere. They always absorb energy to get started and release energy as bonds are formed. But if you end lower than you started, it's exothermic. It's possible for us to end higher than we started. In both situations, I have activation energies, and then my graph goes back down as new bonds form. But if you compare just where you start to where you end, you can tell if it's exothermic or endothermic. Okay, so that's what I mean by lower and higher. Now, guys, mathematically, if we take a low number and we subtract it from a high number, we're going to get a negative delta H. And that's what this table I is telling us, where with endothermic, I'm going to get a positive delta H because I'm doing a big number minus a smaller number. Okay, so that's important. Something else that you might see, guys, if you're given a reaction that's not on table I, you might start seeing numbers or the word energy written in the reaction. And where it's written in the reaction is going to tell you if the reaction is endothermic or exothermic. So exothermic means energy is being released. We're creating energy. Energy is a product. So as far as in a chemical reaction goes, you're going to see the energy written on the right side of the arrow. Okay. In an endothermic reaction, you're putting energy into the reaction in the beginning. Energy is entering with the reactants. So you would see written on the left side of the arrow along with the reactants. Okay, so that's something else. Another way to tell if we're exothermic or endothermic is by, so let's say you don't have a graph to look at, it's not on table I, they didn't give you a reaction and show you which side the energy should be on. The last thing you can do is do the reaction and feel it. So if you have an exothermic reaction, your chemicals are releasing heat. So that heat is leaving chemicals and it's coming out into the surroundings. So think about you. You're in the surroundings. You're holding the test tube, right? There's water surrounding the reaction. What's going to happen to the surroundings if heat is leaving the reaction and going into the surroundings? It's going to feel hot. Opposite with endothermic, right? Those chemicals are absorbing heat. They're taking heat from the surroundings in order to do their thing, in order to change, right? So if heat is leaving the surroundings, the test tube, the water, the air, and going into the chemical reaction, how are the surroundings going to start to feel? They're going to start to feel cold. So if you were holding the reaction in a test tube, you'd be able to feel if it's exo or endothermic from the outside, which is pretty cool. And that's something that we're going to actually do in school too when we see you in person. Okay, so I think that is a list that covers everything. Now let's see what kind of questions we'll have to answer. Question number 1, which solid, NaCl or LiBr, when dissolved in water will lower the temperature? So let's go and look at table I. I want you guys just to notice all of the different types of reactions. They're kind of clumped together. So when you're looking through this table, that should help you find things easier. All of these reactions down here are dissolving. So they're not really reactions. They're showing you when a compound is dissolved in water, if energy is absorbed or released. These reactions here in the middle, they all start with one thing. I'm sorry, they start with two things and end with one thing. So these are just plain synthesis reactions. Sometimes they're exo, sometimes they're endo. And then up here we have hydrocarbons reacting with oxygen to make carbon dioxide and water. So these are our combustion reactions. And you'll notice that these are all exothermic. They all have negative delta H's. So if we're looking for NaCl and LiBr dissolving in water, we want to be looking on the bottom of this list. All right, here I see NaCl dissolving in water. Here I see LiBr dissolving in water. So I see a positive number and a negative number, meaning that this is an endothermic process and this is an exothermic process. I want you guys to tell me which one of these is going to feel cold when it dissolves. All right. And next question, guys. So this is more of an honors level question. I'll kind of let you know what they would expect on the Regents level. So they're telling us that C3H8 is burned completely in O2. So this is a combustion reaction they're asking us to find. And I see C3H8 right here. And I see that the delta H is negative 2219.2. So let me write that down. Okay, so they're talking about 300 grams of C3H8. Now, guys, in a chemical reaction, when a chemical reaction is balanced, the coefficients in the reaction represent moles of that substance that are required to react. So for this reaction, 1 mole of this is propane requires 5 moles of oxygen to create 3 moles of carbon dioxide and 4 moles of H2O. This 2219.2 number is the amount of energy required for those specific amounts of moles. So if I wanted to react 2 moles of propane, then my amount of energy would double the amount of energy being released. If I only wanted to react a half a mole of propane, then the amount of energy that I'm going to release is going to be cut in half because I'm changing my number of moles in the equation. So as far as the Regents goes, that's as complicated as it'll get. This question is a little bit harder because they're not giving us moles, they're giving us grams. So we know how to convert from grams to moles. All I have to do is say, okay, well, if I know what 1 mole of C3H8 weighs, I can do that conversion. So I'm going to look up C3H8 on the periodic table. I'm going to add up 3 carbons plus 8 hydrogens, and I'm going to get 44 grams. Okay. So the question doesn't want to know, though, how many moles this is. It wants to know how much heat is going to be released when I react that many moles. So now I have to take my delta H and say, okay, well, for every 1 mole of propane, I'm releasing 2219.2 kilojoules of energy. I don't want you guys to get caught up in this negative number. You can't release a negative amount of energy. That negative sign is indicating that this reaction is exothermic and that specific amount, that number, is being released. Okay, so when you see numbers written in chemical reactions or when you plug numbers to do dimensional analysis, you're never going to plug in that negative sign. But if you're asked what is the delta H, it's important to write the negative sign showing that that amount of energy is being released. Okay, so I'm going to multiply 300 times 2219.2, and I'm going to divide by 44, and I'm going to find that 15,100, I'm going to round to the nearest whole number, 31 kilojoules of energy are released. Okay, and just to show you guys what this would look like in a chemical reaction, I'd have C3H8 plus 5 O2s yields 3 carbon dioxides, and is it 4 waters? Yes, 4 waters. Since this is an exothermic reaction, the energy would be written here on the end. It could either say the exact number or it could say plus energy. Notice that I didn't write a negative sign. You don't have negative signs in chemical reactions. Putting it on the right side of the arrow is showing that it's being released. Okay, so that's it for potential energy diagrams, exo-endo, table I. Give you some questions and we will talk tomorrow.